everyone. We're going to finish out this chapter by talking about catalysis, which involves catalysts. As an introduction, a catalyst is defined as any substance that changes the speed of a chemical reaction. Typically, they speed the reactions up without undergoing any permanent chemical change itself. And what that means is the substance that I started with at the beginning of a reaction is going to be the same substance that I end a reaction with. So it doesn't change its bonds with anything or it doesn't rearrange itself. Now, why do we care about studying catalyst? Well, a couple things is to help us understand reactions in our bodies. Also, to understand reactions that happen within our atmosphere, such as the ozone layer, and reactions that happen within our oceans, such as pH levels. Now, a couple other reasons is industrial and commercial use in order to create products and manufacture them, and then also how to inhibit or remove catalysts that promote undesirable reactions such as metals corroding, aging within our bodies, and tooth decay. We're going to talk about two different types of catalyst. The first one is going to be homogeneous, and the second one is going to be a heterogeneous. So a homogeneous catalyst is one that is present at the same phase of a chemical reaction. So we learned about homogeneous mixtures all being the same phase. So here we're going to be using the same word. A good example of this is the decomposition of aqueous hydrogen peroxide breaking down into water and oxygen. And it does this with the help of a catalyst called bromide ions. We can also use iodide ions as well. And all of these are in the aqueous phase. A good example of this is the exact one of showing elephant toothpaste. If you are a big fan of watching elephant toothpaste occur, all they're doing is adding a catalyst in order to see this reaction happen quick, and that's how you get your little explosion that everyone loves to see. Again, a catalyst speeds up the reaction without itself undergoing any kind of net change. Now, when we look at a catalyst, it is not part of the overall chemical reaction. Similar to intermediates, they are not going to be in it. So, for example, if we see the equations down below, step 1 and step 2, and we write the overall net equation, you're going to note that we cancel out iodine and then we cancel out IO negative. And what we're left with is 2 hydrogen peroxides in the aqueous phase, 2 waters, and some O2 gas. Now, how do I tell the difference of which one is a catalyst and which one is an intermediate? A catalyst is typically there at the start of the reaction. So here, it's here at the start, and it's also here at the very end, and it doesn't change. So here, I to the negative power would actually be a catalyst. An intermediate, on the other hand, is typically formed during the reaction. So notice here that IO is formed during the first step and then consumed during the second step. So IO negative is actually an intermediate. So that's a good way to tell the difference. So how does a catalyst work? Well, the way a catalyst affects the rate of a reaction is by affecting K, which is our rate constant. Based on the Arrhenius equation that we learned in previous lessons, K is determined by looking at the activation energy and the frequency factor. And so it speeds up a reaction by altering either one of these two things. For example, it can actually lower the activation energy barrier, and this is the typical general rule. And the other thing is it can help with the orientation of reactants to make sure that they are in favorable orientation when they collide. So here's a picture I took from your guys' textbook. The red line shows hydrogen peroxide breaking down into water and oxygen gas without a catalyst. Notice here that my activation energy is very high. So that means the speed of my reaction is going to be typically pretty slow because it takes a lot of energy in order to get over that barrier. Now, if we add a catalyst such as a bromide ion or an iodide ion, notice here that my activation energy is a lot lowered, and this actually happens in a two-step reaction. The other type of catalyst that we're going to talk about is a heterogeneous catalyst, and a heterogeneous catalyst is one that exists in a phase different from whatever the reactant molecules are. So for example, if the reactant molecules were all in a gaseous phase or all in a liquid phase, typically what is introduced is a solid, which is a different phase of matter than the other two. Also, typically that solid is going to be a metal or a metal oxide. A good example of a heterogeneous or heterogeneous catalyst is the formation of gasoline. We actually add a little bit of metal and metal oxides to gasoline called cracking catalyst that help speed up the formation of this. Now, one thing to know about heterogeneous catalyst is that the initial step is that we actually have to prepare these catalysts in order to have optimal results in our reaction. And we usually do this by a process called adsorption. And I put it in capital letters so you didn't mix it up with absorption. So adsorption refers to the binding of molecules to the surface due to it being extremely reactive. And we want as many of these adsorption sites as possible, or active sites as possible, so our reaction can happen to the full extent that it should. Last but not least, we are going to talk about a special type of catalyst called enzymes. Now, the human body is characterized by a lot of different chemical reactions that keep our body running, such as chemical reactions such as digesting food, transporting oxygen through our blood, other things such as sending a chemical reaction and resetting different things within our body in order for things to occur, such as a muscle impulse. And all of these have to occur in very controlled rates to maintain life. We want to keep a balance. So enzymes are there to help this. And enzymes are just a large protein molecule that acts to catalyze different biochemical reactions. And they are very selective in the reactions that they catalyze. A good example of this is catalase decomposes hydrogen peroxide into water and oxygen within the cells of our body, specifically the peroxisomes. Another one that we talk about if you ever take anatomy and physiology is going to be sending a nerve impulse to a muscle to have a muscle contract is done by a neurotransmitter called acetylcholine. And there's an enzyme that actually helps reset that reaction for it to keep going and occur quicker called acetylcholinesterase. So one thing I also want you to recognize is that enzymes usually end in ASE. So ligase, catalase, acetylcholinesterase, all of the enzymes tend to end in ase. Amylase, oh, that's a good one. It helps break down food in your mouth. And last but not least, let's talk about a couple things we see within enzymes. I'm going to be flipping back and forth from this slide to the next slide to kind of illustrate and show you a picture of where these are located. So enzymes have a spot on them called an active site. This is the location where the reaction takes place. And then there are things called substrates. And then substrates basically react with this active site on the enzyme in order for a reaction to occur. Now, substrates fit into this active site like a lock and key mechanism, and so they have to match. If you go to this slide here my green is my enzyme. Over here, this is an active site and this is an active site. So this is where the actual reaction's taking place. And typically a substrate, or substract they called it here, but it's still a substrate, comes in and it bonds to this. And notice that the substrate has a certain shape, and that shape must fit this active site. So I'm going to put substrate because that's how we learn it. Substrate. And they have to fit into this active site. Oops. Now, when those substrates go into that active site, it forms a complex called an enzyme substrate complex. And this is where they have combined and where we have different bonds such as dipole-dipole attractions, hydrogen bonds, and dispersion forces holding them in place while the reaction is taking place. After the reaction is done, the enzyme will release the products, and notice here it split the bond between this compound. Now, one thing to talk about is enzymes are very specific in terms of if you're going to go into pharmacology or drug use, because in order for certain drugs to work, they have to fit in certain active sites or certain enzymes. Last but not least, we're going to talk about something called enzyme inhibitors. These are molecules other than the substrate that is able to bind with the enzyme and block the entry of other substrates. Good example of these are things like nerve poisons or certain toxic metals such as lead and mercury are believed to act this way. Another thing that is common in households is carbon monoxide. Typically, in your blood, you have something called hemoglobin, and that is where oxygen attaches in order to transport it throughout your body. However, carbon monoxide, actually what they do is they bond to the same locations that oxygen would on a hemoglobin molecule, and therefore your body doesn't get enough oxygen, and that is typically how you die of carbon monoxide poisoning. So catalysts and understanding how things react is very important. And that's the end of today's lesson. If you have any questions, please don't hesitate to ask, and I hope you guys have a great day.